Hello everyone again. Welcome to the second talk of this session of CosmoVerse Lectures at your desk. We will now be hearing from Dr. Julien Lesgourgues, who is a professor at Aachen University in Germany. He has studied and is currently studying the properties of dark matter and neutrinos, and he's working on scenarios describing the early universe with an eye to the Hubble tension, a theme that is very dear to us here in Cosmoverse. Among his efforts in cosmology, we mentioned that he has been a member of the Planck Satellite Collaboration and is currently part of Euclid. He also developed the Boltzmann-Solbert class, as probably many of you know, and he also helped developing the sampler Monty Python, both of which are heavily used, massively used within the cosmological community. Among the prizes that he received in recognition for his commitment to our field are a bronze medal for research in theoretical physics by the CNRS back in 2006. In 2018, he won a Gruber Cosmology Prize and a Royal Astronomical Society Award. And back in 2019, he also won a European Physical Society Cocconi Prize for his contribution to the Planck Satellite Collaboration. Finally, he has been invited as a lecturer to several international summer schools in cosmology, and this is a list that now will also include today's lecture on CMB anisotropies as an indirect probe of the Hubble parameter. So please, Dr. Lesgourgues, feel free to start whenever you could.
Thank you very much, Enrico. So the topic of CMB physics and CMB anisotropies is huge, but we will manage to keep it contained today and contained in 1 hour, because we will be focused on the relation between CMB anisotropies and measurements of the Hubble parameter, which is a main topic of Cosmoverse. Okay, so you know that photons were in thermal equilibrium in the early universe, and then at a redshift of about 1090, they decouple. And after decoupling, they travel in straight line. And if we collect the photons that we see that have been traveling in straight line and which decouple all at the same time, they give us an image of a sphere, which is a last scattering sphere. The photons have a black body spectrum. So if we measure the intensity of these photons, we can summarize information by a measurement of one temperature in each direction. We can also measure a polarization, but this will not be important today. And then we can map the temperature in all directions. This has been done by several experiments, most famous being WMAP, Planck, SPT, ACT. And if you project the temperature fluctuations from the sphere to some kind of ellipse, you get these famous maps. This is a Planck map. So mathematically, this temperature anisotropy map can be described as a relative fluctuation of temperature in each direction. Hat n stands for 2 angles. And if you want, you can also expand it in spherical harmonics, and then the information is contained in the ALM. And what we are most interested in as cosmologists are statistical correlation in these maps, in particular 2-point correlation. So if you have the map delta t over t as a function of n, you can build the angular correlation function by looking at every pair of 2 points in the map separated by a fixed angle theta, and then multiplying the temperature anisotropies in these 2 points, doing it for all pairs of 2 points, taking the average, and you get the so-called angular correlation function, which tells you how correlated these points are as a function of the separation angle. So this is in real space. You could do exactly the same in harmonic space. Harmonic space is like Fourier space, but usually you go to Fourier space when you have a 3D distribution. You go to harmonic space when you have something defined on a sphere. So the equivalent process in harmonic space consists in taking these ALMs and taking the average over all the ALMs for fixed L, because L refers to angular separation, averaged over the values of M, which account for different possible orientations. And you build these CLs, which contain the same information as C of theta. They could both be used for measuring the cosmological parameters. The CLs are more popular because they give kind of more focus on interesting phenomena. They give more focus on the features which really encode the cosmological parameters. So these CLs have a very famous shape that you have seen with, so these are the CLs normalized in some way as a function of multiple L. For different models, in all my plots, there is a reference model in black, and the red curve show what happens when you vary one of the cosmological parameter of the lambda CDM model. So we have this plateau, we have these oscillations, which have a very precise shape. And we see also that when we vary the cosmological parameters, the impact on the spectra, on this harmonic power spectrum of the CMB temperature, are very different from each other. Which is one, the CMB is called the Rosetta Stone of cosmology. It encodes independent information on many different parameters, accounting for different effects in the evolution of the universe. And in principle, once you have measured this curve, you can measure independently a large number of cosmological parameters. So, to understand the details of this curve would take a lot of time. It's the purpose of CMB course. Usually when I teach CMB physics and I want to explain these curves, I use between 4 and 15 hours. We don't have time for this, but we don't really need it because I'm going to show you that if our goal is to understand how to go from this to an estimate of the Hubble parameter, then we don't need to understand the details. We only need to understand why there are some peaks on this curve. And that's what we are going to do now. So here is a plot on the left trying to summarize what's going on and what gives rise to the peak. The vertical axis is time flowing from the very early universe until today. And in this very schematic plot, in the vertical axis, I'm accounting for one spatial dimension. So the universe starts very early with inbuilt fluctuations of density. I represented it in a very schematic way by these red and blue blobs. They are supposed to account for the fact that even after inflation, you already have random fluctuations in the universe. My blobs are really simplistic because they are spherical, they all have the same size, while in the real universe, you have fluctuations on all scales, all superimposed to each other. So if you would take a picture of the real universe, it would look a lot more like in the CMB map that I have here in my back, with lots of structures, large-scale structure, small-scale structure, etc. In the early universe, before the time of decoupling, which is here, the photons are in thermal equilibrium with other species, especially they remain in thermal equilibrium very late with baryons. And so the thermal bath forms a fluid which has pressure. It has pressure because photons are relativistic, so they have relativistic pressure. Now, you know what goes on in a fluid with pressure. You have propagation of density waves, like in the air, like for sound. So density waves are also called pressure wave or sound waves. And if we have overdensities in the early universe, they are not going to stay still. They are going to propagate, and it's really a propagation of sound. It's not the same as sound, it is sound, because it's a pressure wave. So in this scheme where I have one dimension of time and one dimension of space, the trajectory of my acoustic wave emitted by a given point in two opposite directions could be accounted for by two lines. In reality, they would not be horizontal. It depends how what measure of time and space is. I mean, they would not be straight line, but they would be lines. And the distance between the axis and this line is called the sound horizon. So the sound horizon is just the distance traveled by photons between the very early universe and the later time. And then at some point, our photons decouple. And when they decouple, they have traveled by the sound wave, meaning that the feature that was here in this point has sent information in these 2 points, and these 2 points are correlated. If I had initially an overdensity here, I will keep track of this overdensity in these 2 points. If I had an underdensity, I will keep track of this underdensity in these 2 points. Then the structure that we have here on the last scattering surface is frozen, and some photons travel in straight line from the last scattering surface to us, giving us information on what was the value of the overdensity or the temperature fluctuation in these different points of the last scattering surface. They travel by some distance. We measure them today, and we expect that if we look at points separated by twice this sound horizon, they will be correlated. They will either be 2 overdensities or 2 underdensities. So we expect that in the map of CMB temperature, there is a correlation under an angle given by 2 theta s, where theta s is the angle under which we see the sound horizon at decoupling. And if we put this into equations, what we measure is the angle theta s under which we see this sound horizon divided by the distance to the last scattering surface. Here I am using comoving distances for simplicity. On the numerator I have the comoving sound horizon, and on the denominator I have the comoving angular diameter distance to last scattering. The comoving sound horizon is just given by an integral over the sound speed in the tightly coupled thermal bath photon baryon fluid integrated over conformal time between the very early universe and today. The angular diameter distance is given by a similar integral that we will see in a few slides. It's an integral which is running from the time of decoupling until today, and it's also an integral over conformal time, but just without the sound speed. It's the integral from decoupling until today of just d eta, the increase in conformal time. So the ratio between the two gives us theta s, and if I expand my map into multiples, I will take your question in a second. If I expand my map into multiples, I expect that the multiples will keep track of this correlation if we satisfy the relation pi over L equals theta s. Because what is a multiple L? It's a template on a map where we have an angular separation of theta between adjacent minima and maxima, which means that we have an angular separation of 2 theta between maxima. And that's exactly what we expect from this drawing. So the multiple corresponding to the first peak here should be given by a value of L fulfilling pi over L equals theta. The other multiples are just the harmonics of the first one. Like when you do an expansion from real space to Fourier space, if you have a correlation at one scale, you will see regularly spaced harmonics in Fourier space. It's the same in multiple space. You will see all the harmonics of the first peak at n, for the nth peak, n times pi over L. And I'm very pleased to have already a question. I forgot to say, like Tamara, I really like to be interrupted for question. So P. Ali, please ask your question.
Yeah, my question was actually what you were just covering. So I wanted to ask, like, what the subsequent peaks beyond the first peak correspond to. So the first peak, I'm guessing, corresponds to like the distance the sound waves travel between the basically after the Big Bang and recombination. Divided.
So they all correspond to the same thing, to the sound horizon.
They all correspond to the sound
just the harmonics of the same thing. If we would not use the harmonic spectrum, but the angular correlation function, which is here, we would see a single peak. When we go from angular space to harmonic space, the single peak will give different harmonics and they will be regularly spaced. An intuition that you can have about this is that if I have a correlation between these 2 points,
Yeah.
Then I have a contribution from Fourier modes, which have a maximum here and a maximum here, but also for Fourier mode with a smaller wavelength, with one maximum here, and one here. Or I can always subdivide this interval in 2, 3, 4 chunks, put many wavelengths here, and they will all correspond to configuration where I have one maximum here and one maximum here. That's how the different harmonics pop up. But
So
all
that
the
means
harmonics come from the same physical mechanism, which is this sound horizon correlation.
so does that mean that like all the peaks in the CME power spectrum will all be at integer multiples of the first peak?
Exactly. They will be at integer n, where n is the number of the peak, multiplied by pi over L.
Yeah, so the first peak. Okay.
Yeah. Very
Okay.
good. All right.
May I also have a question?
Yes.
So the light scattering surface is not exactly, I would say, a perfect like two-dimensional
Yeah.
surface. It's gonna have a certain thickness, right? And
Yeah.
how is that gonna affect like the theta as the estimation of this angle?
Yeah. So the fact, what you are saying is that the photons do not decouple instantaneously. They decouple over a range of time. And this introduces a bit of broadening of the peak. It's not changing the maximum of the peak, but it introduces a broadening of the peak, as well as other effects. It is responsible for the fact that you have an exponential tail at high L here. This comes also from a kind of smoothing effect corresponding to the thickness of the last scattering surface. Yeah. Very good. So, the temperature map is not all what we have. We have also a map of polarization of the CMB photons. And by estimating the degree of non-Gaussianity in these maps in different points, we can even measure a third map, which is a map of CMB lensing. It tells you in each direction how much the structures are magnified by gravitational lenses. For each of these maps, we can measure a spectrum, and what we saw before was only the spectrum of temperature. There is also a spectrum for polarization. In fact, there are two, but so far we measure only one. There is a spectrum for lensing, and there are also some cross-correlation spectrum. This will not be important for us today. You will see that the only important thing will be the peaks in the temperature. But it's worth mentioning that all these things have been measured, that the measurements from Planck and W map, which overlap at low L, are extremely consistent to each other. And at large L, we have redundant measurements by Planck and two recent extremely accurate collaborations, the South Pole Telescope and the Atacama Cosmology Telescope, and they also confirm each other. They also agree very well. Yes, question by Piali.
Sorry, I just wanted to understand. So in the top left panel, it looks like the first peak is around LF 220-ish.
Yeah.
And
around 200, yes?
200, yeah, okay. But the second peak isn't at 400?
That's a very good point. Actually, that's a refinement to which I will come at the end.
Okay.
The reason for which the peaks are not exactly multiples of each other, it's like more advanced. I'm starting from the simple ingredients, and then I will give you a more refined point of view towards the end, and you will understand why the peaks are not exactly regularly spaced.
Okay, thanks.
Very good. Yeah. Okay, so we have some redundant measurements from Planck W maps, SPT, ACT, they all agree with each other. And then when we try to fit these spectra with theoretical predictions, if we only use CMB information, we get extremely good fit with a minimal lambda CDM model with 6 parameters. So that's impressive because, as you can see, we have thousands of independent measurements. So fitting thousands of independent measurements with 6 parameters is a big success, of course. And moreover, this best fit you do to the CMB agrees very well with other measurements from Big Bang nucleosynthesis, remote supernovae, full shape of the large-scale structure power spectrum, which have larger errors. But now, the reason for which we are here is that there are inconsistencies or apparent inconsistencies with other types of experiments, like the measurement of H0 from distance ladders, the measurement of the amplitude of the power spectrum, S8 or sigma 8 from Will cleansing, and since a few months, even with a measurement of the sound horizon in the spectrum of galaxy from DAISY. And so that's why we are here. We want to understand then the robustness of each experiment, and one thing you could say is, what if there is a problem on the side of the CMB? So, what is not so nice in the CMB measurement? What is more complicated than you may think at first sight? Well, mainly it's the fact that we have foregrounds. What our instrument measure is not a pure CMB, but it's a CMB contaminated by other sources of photon emission, which could be confused with a CMB if we are not careful. I show you, for example, here, the maps obtained from by the Planck satellite in 9 different frequencies. In all these maps, the intensity has been converted into a temperature, assuming that you would have a pure black body. So if indeed we had a pure black body, then these 9 maps should all look exactly the same. And obviously, you see that they don't, which proves that on the top of this black body, there are some other signals which have different frequency dependence. So all these maps are oriented such that the horizontal plane is a galactic plane, and you see that most of the issues come from this plane. If we go away from this plane, and if you look at all the map from here, 44 gigahertz, all the way to 270 gigahertz, then you see that most of the patterns you see are really identical, which already makes you understand that this is where the CMB signal is. If you remain far from the galactic plane, but you go to very low frequency, it starts to look a little bit different. If you go to very high frequency, it's completely different. The original structures are completely masked. And if you look at what happens in the vicinity of the galactic plane, then all the maps are different from each other. And this is a hint that most of the foregrounds come from our galaxy. And so what can you do with this? You can try to make a physical model of all the expected contributions in this frequency range. For each of them, you get a model, you get a template with a few free parameters. And then you try to do a joint fit of the superposition of all these templates to the map in order to measure the free parameters that describe typically the amplitude and the property of each foreground. And after that, you look if you get residuals or if you have been able to account for your full map. So this is what people have done in many collaborations for many years. And one way to summarize it is this famous plot showing the frequency dependence of different signals that mix up in CMB measurements. The CMB signal, which is a black body, has this shape, characteristic of a Planck spectrum, black body spectrum. But you see other signals, thermal dust, free emission, synchrotron emission, which comes from the fact that charged particles are deflected in the magnetic field of the galaxy, spinning dust, etc. So when I was in the Planck collaboration, I studied all these things. Now I must say I forgot a lot about the physics of foregrounds. But the most striking is that there is a range where the CMB dominates. So you already know that if you focus at the central frequency bands, you will be dominated by the CMB, at least in some regions of the map. And that's exactly what we saw in the previous maps. If we look from 44 to 143, meaning from this map to this map, we really see the same patterns far from the galactic plane. But if we look at very high frequency or very low frequency, we are dominated by foregrounds. And this would be the case here or here. This plot does not contain all the information because at the end, what are we trying to do? We are trying to measure this correlation function. So it's nice to know that there are foregrounds, but we need more. We need to understand if these foregrounds have angular correlation or not. Depending on their angular correlation, they could contaminate the CMB spectrum or not, and at different multiples. You could imagine that for a given frequency, for a given foreground, you expect correlation on very large angles if you have a very big smooth pattern, or on very small angles if the coherent length of the phenomenon giving rise to the foreground is a very small scale phenomenon. So there is another information on the foregrounds which is represented in this map, which shows roughly the C of L of each contamination, so the harmonic power spectrum as a function of multiples. And we have different curves here corresponding to the foregrounds that we have seen before, and most of them increase with L, meaning that the foregrounds are mainly a problem at small angular scale, large multiples, with the exception of this dust contribution, which has the opposite behavior, which would tend to contaminate mainly the small L's, the large angular scales. You could get a plot like this for each frequency channel. Here we choose the 143 frequency channel, which is the one where the CMB dominates the most, and that's why all these curves are very low. If we would do it for other frequency channels, the overall spectrum of the foreground would be higher. There is also here a contribution from noise, because foregrounds are not the only problem in CMB analysis. You have to model noise. You have noise from the instrument, it can be just the electronic of the on board the satellite, or the cryostats, which has variations. The temperature of the satellite can vary. There are pointing errors related to the fact that your satellite tells you that it's looking at one direction in the sky, but it might be slightly off with respect to what you think. There are beam errors, which come from the fact that, for instance, an experiment like Planck is not really measuring the temperature in one point, but the averaged temperature in one small region with a non-trivial shape. This will need to be taken into account when you will go from the time-ordered data to the map. You have issues with cosmic ray glitches. You have also errors introduced by the fact that at some point you want to get rid of the information which is too contaminated by the foreground, so you impose a mask on the map, meaning you just cut out anything which is too close to the galactic plane. But introducing a map with a non-trivial geometry will introduce correlations between your multiples. So there are lots of non-trivial effects to be taken into account, and this would be a summary of the spectrum of the noise, and the spectrum of the noise increases always with a multiple, so it's always more difficult to measure very small scales than large scales. But the crucial thing that we want to say here is that suppose that in spite of many experts having worked on this for decades with very sophisticated algorithms, with a lot of redundancy, there is a competition between experiments, there are competition between different teams inside an experiment, everybody tries to propose his method, his pipeline. Despite of all the checks that have been done, suppose that there would be an issue in the way in which a CMB experiment models the noise or models the foregrounds. If this was the case, the measurement you would do of the large L temperature spectrum might be a bit wrong, because this is where the noise and the foregrounds become important. And even worse, in the measurement of the spectrum of polarization, you might have more issues, because in the spectrum of polarization, the foreground contamination is higher, and you have foreground contamination at many multiples. But if your goal is to measure the scale of the first peaks in the temperature power spectrum, In this case, you could even not try to model the noise and the foregrounds. They are not contributing, they are not changing the measurement at the scale of the first few peaks. And I could see it in the Planck collaboration. It was very striking. I was a theorist, so I was just watching the talks from my experimental colleagues during the whole collaboration. And I remember at the very beginning, they came with the first data, and they had not tried to clean foregrounds and noise. And they said, this is the raw data if we plot it and if we measure the power spectrum. And immediately the first few peaks were as we see them today. And then there were years and years of analysis in order to improve measurements by better models of noise, better models of foregrounds. And as a consequence, the measurement of the high multipoles changed a bit. But the measurement of the shape of the spectrum for the first few peaks never changed. You would get it even if you would measure it from the raw map with no foreground cleaning and no noise modeling. So this is why, if you are only interested in measuring the scale of the first few peaks, it's incredibly robust. You don't need to account for any complication. It's a pure geometrical measurement. It comes directly from your data. All right. So now comes the second part of the talk, in which I want to explain how you go from this measurement of a correlation angle in the sky, theta s, into a measurement of the Hubble parameter. So we say that the quantity we try to measure is this angle, which is a ratio of the comoving sound horizon at the time of decoupling over the angular diameter distance to decoupling. Each of these distances is given by an integral. As we said, in the sound horizon, the integral contains the sound speed, in the angular distance, not. Here I did a change of variable from conformal time to redshift. And this is why I now have the evolution of the expansion rate, h, a dot over a, as a function of redshift. It comes from my change of variable. When you write an integral over conformal time, the fact that the expansion rate matters is hidden because you have hidden it by going to conformal time. If you go back to a variable like redshift, it appears explicitly. So on the numerator, we integrate over the sound speed divided by the expansion rate between the redshift of decoupling and infinity. Redshift of infinity, of course, corresponds to very early universe. While on the denominator, in order to get the angular diameter distance, we integrate over the inverse expansion history from us to the redshift of the last scattering surface. Yeah, Sotiris, please.
Yeah, sorry, what is Z tilde? Z tilde?
It's a dummy variable. I did not use Z because Z was taken here as a...
But just for integration, sorry.
It's just for integration, yeah.
Sorry.
Okay, so it is this ratio that we measure. So the measurement gives us theta s, and as we said, it's a pure geometrical measurement, independent of foreground and noise modeling in CMB experiments. And then we want to measure cosmological parameters from it. And I'm going to tell you how to do this in details, but the overall idea is that you have different ways to infer what the numerator is, either by using other information in the CMB, other than the scale of the peak, or by using independent experiments, like we will see BAO, BBN, BBN, etc. And it gives you the numerator with a small model dependence. You need to do assumptions in order to do it. For the denominator, if you want, once you have measured theta s and once you have predicted your numerator, you want to adjust cosmological parameters such that the denominator will match. And the parameters that will be relevant are all the parameters which play a role in the expansion history between decoupling and today. These are H naught, these are maybe dynamical dark energy parameter, omega lambda, omega m, neutrino mass, etc. And in particular, if you are in a given model like lambda CDM, And if you have enough constraints, then this will give you a way to measure H0, but it's a model-dependent way. It has a strong model dependence. And this is why people keep repeating that the CMB is not measuring H0, it's measuring theta s. And it's only once you have assumed a model that you can turn it into an indirect but model-dependent measurement of H0. And I'm going to see you explicitly how you can do it for lambda CDM and give a hint of how you can do it for extended models. So let's elaborate a bit on this integral and let us see how the different pieces in this integral depend on cosmological parameters. For this, I will not immediately assume lambda CDM. I will just assume a very general cosmological model where I believe our standard model for Thomson scattering of photons over electrons, for decoupling, recombination, I assume that the thermal history of the universe was like in standard cosmology, but I don't yet assume specifically lambda CDM. Then I know how to compute, for instance, my sound speed. It's very easy. The sound speed is a sound speed in the photon baryon fluid. It only depends on one quantity, which is the density of baryons relative to photons in the universe. Only one parameter. What about the redshift of decoupling? The redshift of decoupling is something you learn to compute in a course on the thermal history of the universe. It's almost fixed by our knowledge of the hydrogen atom. You cannot change it a lot unless you introduce very exotic assumptions. But still it has a bit of different dependence on parameters. It depends a very little bit on the primordial helium fraction, because the decoupling of the photons does not depend on all the baryons in the universe, but only on how many free protons are left at that time. It depends a little bit on omega b over omega gamma, because the question is, when do photons stop to photodissociate hydrogen atoms? And this depends on the balance between photons and electrons or protons in the universe. It depends a little bit on omega m, where small omega is a big h square for me, because decoupling is when the Thomson scattering rate gamma is equal to the Hubble rate h. If you want to estimate this time, you also need to know what is evolution of h during matter domination, because decoupling is during matter domination. So there is a bit of dependence of omega m. I must say, this dependence is mainly logarithmic. The redshift of decoupling only depends logarithmically on these parameters. But then the last question is, on which parameter does the expansion history depend? And this is model dependent. So to make progress now, I'm going to take one more step and assume specifically lambda CDM. And then I know that my h of z is given up to a factor with some dimension by cosmological parameters, weighting the contribution from the cosmological constants of non-relativistic matter and of radiation. So you recognize a famous scaling factor, and what appears here is always a combination big omega h square, which I can also denote as a small omega. And if I am in a lambda CDM universe with zero curvature, I know that omega lambda is 1 minus omega m, up to very good approximation. So I'm going to substitute this h of z in my expansion rates. But when I am in the numerator, I know that I only need to take into account matter and radiation domination. I can neglect lambda domination. So I neglect the omega lambda term. When I am in the denominator, I integrate from me to the last scattering surface. So since decoupling takes place during matter domination, I can neglect radiation domination. So I have the term for lambda, the term for matter, and moreover, using this relation here, I simplify a bit and I get this. And I have highlighted in color the dependence on the remaining parameters. I did not put a color for omega gamma because it's completely measured by the temperature of the CMB. I did not put a color for omega of radiation because if I am in the minimal lambda CDM model, I know that radiation is just photons and 3 active neutrinos. And I know what is the relative contribution of the neutrinos So my omega r is not anymore a free parameter. So I'm left with 3 free parameters, omega b, big omega m, and h squared. Or you could say small omega b, small omega m, and h squared, but always 3 independent combinations. So if I have measured theta s with a CMB, I have a relation between 3 parameters. And I still need to measure independently 2 of them in order to get a measurement of the third one. And there are many ways to do it. This is a most busy slide. How do I know omega b? I can learn omega b from the shape of my CMB spectrum by looking at the ratio of odd and even CMB peaks. It's a very robust measurement because it depends only on the first 3 peaks. So even if there were problems with foregrounds, it would not contaminate this measurement significantly. But if you are a CMB skeptical person and you say, no, now I don't want to use a CMB anymore, you can also estimate omega b from the measurement of the abundance of deuterium in the early universe. And then using a BBN model and some very robust arguments, you will get another measurement of omega b. And these two are known to agree very well, so at the end you will get a similar result. Then you can try to measure the parameter small omega m directly by looking at the ratio of just the first and the second CMB peak. This is very dependent on omega m. And again, you could be a CMB skeptical person and say, no, I don't want to do this, and estimate small omega m from the full shape of the galaxy power spectrum from Bose and Daisy, for instance. That's not very accurate. So maybe you want to think of other independent ways. And there are many ways now to measure big omega m by using information from baryon acoustic oscillations and or information from supernovae, not the distance ladder supernovae, but the remote supernovae. Or by using information from cosmic shear, from DES, for instance. So there are many ways to know omega b and omega m independently. And once you plug this information in this relation, and you use this relation to measure the third final free parameter with this h, whatever information you have used from here, you will always get a small value of h naught. Even if you have used the CMB information only to measure theta s and not for the other ones. So that's our problem. That's why we have this problem of being unable to account for the results from shoes, but that's in lambda CDM. And more generally, I should stress that really in order to come to here, we had to make an assumption on the sound horizon, on the fact that it's described by this standard sound speed. We had to make an assumption that we know how to compute the redshift to photon decoupling, and we had to make an assumption on the early and late expansion history. As soon as you make a modification to one of these ingredients, the same measurement of theta s by the CMB will return a different range for h naught. That's why it's a completely model-dependent measurement. Yes, Piyali.
So I wanted to ask, like, with regards to the redshift of decoupling the ZD parameter.
Yeah.
I was just wondering, when we have like so many accurate spectra in so many different sky directions, why you can't see the like a spectral feature corresponding to you know, the 13.6 EV ionization energy of hydrogen, which will tell you exactly.
We don't see spectral features in the CMB. We only see a perfect black body. To see spectral feature, people have thought of experiments. There have been Project Pixie and others trying to look again at the CMB with an amazing resolution in order to go beyond the black body picture. And there, you're right, you expect to see things like emission lines from recombination. We don't have it just because it has not been funded. We could in principle. Yeah.
Okay, so in the future, it might be possible to see like the spectral lines corresponding to the recombination.
If you manage to convince NASA or ESA or JAXA, then in principle you could.
And then you would know
it's an expensive measurement. It requires a very, very high accuracy, but it's doable. We would have like, the technology. Yeah.
But I'm just trying to understand, like, theoretically, do some of the solutions proposed solutions to like the Hubble tension, do they modify ZD?
We are coming to this in the
Okay.
next slides. Very good. Thank you. All right. So now let me just stay in lambda CDM for one more slide, and then we will try to go beyond. So what do we see? We have measured theta s. Suppose that you take some information on omega b and omega m from what we said before, from the previous page. And then you only have one parameter h to adjust. And you can always adjust it in such a way to reproduce theta s. And to get a flavor of how you should adjust h, let's assume that we fix omega b and we fix small omega m, and we increase h. What happens to theta s? If we fix small omega b and small omega m, you see that zd is fixed, sound speed is fixed, this quantity in the numerator is fixed, so the sound horizon is fixed. The only thing you can play with is this h here. And this h is going to adjust the denominator. So if you increase h, so the h increases here, so the integrand decreases, so the denominator decreases, so theta s increases. So increasing h leads to a bigger angular scale of the sound horizon in lambda CDM. It would be the same if we had picked up experiments measuring small omega b and big omega m. Because in this case, you would still have the freedom to vary h here, 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 and here. So there would be many effects of varying small h at the same time. But because omega r is fixed, the variation in the denominator would be larger than the variation in the numerator. And again, the main effect would be that by increasing h, you decrease this integrand and you increase theta s in all cases. And every time you see plots where people fixed all cosmological parameters but h and increase h, you always see the peaks moving to the left. Why? Because you have increased theta s, so you decrease the multiple under which you see the angular scale of the sound horizon. And this discussion will now give us a flavor of what happens if we go to extended cosmology. Suppose that I want now to account for shoes. So I want to have a way to increase h, but keep theta s fixed. In lambda CDM it's not possible, theta s would increase. So I need something such that when I increase h, I either decrease my numerator, such that theta s does not increase, or increase my denominator, such that theta s does not increase. Two ways. Let's be more precise. What can we do? The first approach is to say, let's leave our expansion history in the late and early universe completely unchanged, and let's just try to play with this integration boundary ZD. If some exotic physics increases the redshift of recombination, then this integral has a smaller support, this one has a larger support, and I can compensate for the increase of h, go back to the same theta s. And for this, if I want to increase ZD, I want recombination to take place earlier, so I want a mechanism that speeds up recombination. Second possibility, I don't change my thermal history, ZD is fixed, but I play with the expansion history at early times. I add exotic species, maybe additional relativistic relics with an n effective, maybe something else that contributes to this parenthesis here. So by doing so, I increase the parenthesis, I decrease my integrand, I decrease the numerator, and I can maintain my theta s fixed. Third possibility, I play with the expansion history at late time, but then I must do the opposite. I must find a new ingredient that will decrease the function in the bracket. This will increase this integrand. So then in this case, I will increase the denominator, and again, I am back to the initial theta s. So with any of these three solutions, I could make my CMB measurement of theta s compatible with shoes. How do we do it in practice? Well, people have imagination, have proposed lots of things. To speed up recombination, they say, yeah, I will take your question at the end of this slide, Morteza. In order to speed up recombination, they say, okay, maybe recombination is not a homogeneous phenomena. We have patchy recombination. You can do it if you assume primordial magnetic fields in the universe with big amplitude, but on small scales. You could think of a variation of fundamental constants. You could say, the electron mass depends on the wave of a Higgs field or something, which is not completely stabilized like in the standard model of particle physics. And maybe I had a decrease in the electron mass by 0.5% between decoupling and now. In both cases, you would speed up recombination in the right way. How do you enhance the expansion at early time? With additional relativistic relics or with early dark energy? How do you deplete the expansion rate at late time? Well, maybe dark matter is decaying, so you have less dark matter than what you would think. Or maybe you should replace the cosmological constant by phantom dark energy, because then it pops up very, very late, and overall, it does not contribute to the expansion rate as much as a cosmological constant, and not over such a long range of time. You could have dark matter decaying in dark energy, that would do the same. All these models would solve the problem beautifully if our only measurement was a measurement of shoes and of theta s from the CMB. But sadly, we have a lot more information. We have information on the shape of the CMB spectrum, on the shape of the matter power spectrum, on supernovae, on weak lensing, etc. And the problem is that all these mechanisms will also introduce additional effects on these observables. For instance, the third assumption is very difficult to make compatible with measurements from the luminosity of distant supernovae and BAO. The problem there is very constrained. It's very hard to reconcile all these measurements of the late expansion history. The second mechanism, where you have additional species in the early universe, will typically distort the shape of the CMB and matter power spectrum. And so you get a problem. The first category of model is not yet so clear, but they tend to enter in conflict with both types, shape of the CMB and measurement of omega m from supernovae and BAO. So this problem is extremely difficult. Nobody has a really good solution. Solution 3 seems really very compromised, although not everybody agrees with this. Solution 1 and 2 could be cured, but at the expense of having additional ingredients. You also add physical ingredients that will change the evolution not only of the background, but of the perturbation. And then maybe you will cure the problem and you will get back in agreement. But it's a very difficult thing to achieve. There was a question before.
Yeah, by the way, sorry to interrupt, but I think we have just over like 5 minutes left to presentation.
Yeah, that's fine.
So if that's okay, we'll keep questions for after.
Okay, very good.
Yeah, sorry about that.
Okay, so people have tried. This is a summary of one of our Hubble Olympics paper where we try to confront many of the scenarios of the different categories that I described before to the data. And these black lines are the value of H naught that we get when we test many of these extensions to the minimal cosmological model. We confront these extensions to Planck, SPT, BAO data, supernovae data from Pantheon. We can try other also combinations. And in these models, H naught can increase a bit, but not all the way to shoes. And the reason is that we have these other measurements. If we only had theta s, it would be trivial to solve the problem. But we have these other measurements, and they always put a limit to how high you can go in H, and they prevent you from reconciling all the data. And this brings me to my conclusion. There will be a post-conclusion if I have a few more minutes, but I could even stop here. And my conclusion is, so sometimes when people talk about the Hubble tension, they say, okay, we have three possibilities. Either the measurement of H0 from distance ladders is wrong, or the measurement of H0 from the CMB is wrong, or we need a new cosmological model that will reconcile the two. And that's really not the right way to put the question, because the CMB is not measuring H0. It's measuring theta s. And then you get H0 from theta s with very convolved and model-dependent arguments. So the question you should ask instead is, either distance ladders are wrong, or we need another cosmological model, or the measurement of theta s from the CMB is wrong. That's a good way to formulate the question. And given what I told you, that the theta s is a geometrical measurement which is immune to issues in the modeling of foreground and noise, people cannot think of any way in which its measurement of theta s could be wrong. And that's why I believe the answer to the rightly formulated question is no. Nobody believes how or can conceive how the measurement of this angle in the map could be wrong. It's just measuring an angle. So the two options left are theoretical explanation, new cosmology, or issues in the distance ladders, which I acknowledge is also extremely difficult to conceive. And so also I see very often people complaining in conferences that CMB people are arrogant because they always say that if there is an experiment to be blamed, it's not theirs, it's other experiments. But actually, I don't think people in the CMB community are convinced that we did everything in a robust and correct way. There is still room for the fact that we have missed foregrounds or modeling of noise, modeling of systematics. It's totally possible, but it's just that if we did, it would be irrelevant for the Hubble tension because it would be irrelevant for the measurement of theta s. And the reason for which CMB people may sound arrogant is this. It's because they believe so much in theta s, because theta s is completely immune from the rest. So that's my conclusion, and I will stop here.